All right, welcome. I'm going to give a talk on how Spotify uses Nginx for our audio storage, and in particular how we do that with a sort of sharding algorithm that we apply. My name is Niklas Gustavsson. I work as a team lead for a team of backend engineers, the team that works on basically the audio playback in Spotify. I've been at Spotify for about 3 years. And in general, I'm very much of a distributed systems geek, so I sort of like to work in this area. If you have any questions, feel free to interrupt at any time. I'm happy to take any questions, and hopefully I can answer at least some of them. But to start out, anyone here who's a Spotify user? A few? Anyone who's never heard of Spotify or has no idea what it is? None. So I'll not do the actual, very much of background then. We're a music streaming service, and we have somewhere in the neighborhood of 40 million active users and more than 20 million songs. And we add somewhere in the neighborhood of 20 or 30,000 tracks per day to our catalog. We have, much like if you saw Adrian's talks earlier, we have a very much of a microservice architecture. We don't actually call it that, but it very much looks like much of the stuff that people now describe as microservices. And we've had this for a long time. So basically our backend is broken down into a large set of smallish services. Some of these small services might actually be fairly large because they deal with very complicated problems. Like our playlist service, for example, which is basically a distributed versioning system and therefore is a fairly large code base. But in general, most of our services are just a few thousand lines of code. We have, from a user experience point of view, we really want to have a low latency and high audio quality experience. So we want music to start streaming within 250 milliseconds or so of pressing play. And that is both for the cases where we can actually try to predict what the user is going to play next, and for the completely random stuff that the user does. Just start interactively play. Double-click on something in our clients, and we should have audio data at that client within those 250 milliseconds. We can have a sufficiently large buffer and start playing audio. So this turns a lot of what my team works on basically into large content distribution problem. And you've heard several people mention Netflix so far, and we're lucky enough to not, we only have audio, which is much less bandwidth consuming than video, obviously. So we have a sort of nicer problem than Netflix does, but we instead, I shouldn't say instead, but we have a very large focus on low latency, meaning that we really need to push content to the user in an efficient way. Again, this turns into a distribution problem, and we use multiple mechanisms for that. I'm going to go through some of them. But to start, we have an origin where we store all our music files. We call this master storage. I'm going to mention this a few times. In reality, it's Amazon S3. So that's where we store all our transcoded audio files. We have a separate storage for the original files that we receive from music labels, but those are not publicly available for users, obviously. On top of master storage, we use a number of commercial CDNs. We are not, at this point at least, using our own CDNs or what is a classical CDN like Netflix does. We use multiple commercial providers, and we basically benchmark them against each other using the best provider for any given use case. So if one provider is better in Australia, we'll use that provider in that area, or at least give that provider an additional amount of traffic. To keep a competitive, to keep a competition in between providers, making them work to improve our user experience as well. CDNs now actually makes up the largest part of our content distribution, and that means that we have offloaded a fair amount of our own data centers using CDNs. And they're also very good because they have the servers obviously closer to the user than we can do at this point. We have 4 data centers, so we can only get so close to the user. But there are some use cases where CDNs doesn't work that well for us, and that's where we use our own storage, which is going to be the topic of today's talk. And we call this production storage. There are basically 2 major use cases where we use production storage. Either it's because we are actually closer to the user or closer from a network perspective, and that is that it's in some area we can do peering or get really cheap transit, which makes it financially useful to use our own storage. But the major use case is that for long tail. So music is we have a inception distribution of requests to our audio storage, meaning that there are a few songs which a lot of users play. And then there's a long tail of stuff which is less frequently used. But we still want this very low latency experience for the long tail as well. Problem with the commercial CDNs is they offer a somewhat small data set that we can fit into the servers. And we're also competing against any other user of their servers. So for the long tail, we find that we need something else than the commercial CDNs. And our own storage works well for that. And it's really designed to handle a very large data set. And that's what this talking is going to be about, how we do that. So I don't know if it's visible on the slide, but around the production storage, there's a square showing that this is in one of our data centers. And like I said, we have 4 of these data centers. They're actually deployed into multiple smaller sets as well. Yep.
Can you tell where you have the data centers?
Yeah, sure. We have one in Stockholm, Sweden, and we have one in London. We have one on the US East Coast in Ashburn, and one on the US West Coast in San Jose.
Did you say the master storage was in AWS or was it in
That's,
Fadvice?
yes, it's in S3, Amazon S3, on Ireland, actually. Well, to sort of spin on that question, we at this point only use our own physical hardware. We don't do production deployments into any cloud service, apart from CDNs, but not using like VMs in a cloud service. All right, so then on top of this, we have the Cs in this diagram are showing clients, and they're making requests to these various content distribution mechanisms. When it comes to the production storage, we actually have another backend service in between, which serves as a perimeter service. AP is short for access point. It's basically a content router. So any request from a client will go through the access point, which will take care of authentication and rate limiting and stuff like that before that request goes to production storage. And both production storage and the CDNs are read-through caches. So if we make a request for something which is not available in that, they will go to the origin, fetch the file, cache it on the way back. And to decide on where an individual request goes, we actually have a separate service not pictured in this diagram called storage resolve, which has a large rule set saying that users in this area should get this storage. Users in this at this ASN should have this storage, and so on. And trying to optimize for the user experience. So then let's go into how we actually use Nginx. So production storage is a somewhat large Nginx cluster. It's a little bit more than 300 servers. It's actually divided into multiple separate clusters, each being somewhere in the neighborhood of 50 servers. Why do we use Nginx for this? We basically just wanted a stable web server that always will work for us and that will scale. And scaling, in our case, is largely how much we can push out of each server. Servers are commodity servers. We fit them currently with 11 terabytes of disk, RAID disks. And Nginx will serve as a caching reverse proxy on top of those disks. I'll go back into a little bit more details on how that actually works. So the data set, we have, like I mentioned before, we have in the neighborhood of 200 million tracks, actually a bit more than that. And each of those are transcoded into multiple different bit rates and formats. Each of those files are somewhere in the neighborhood of 5 megabytes in file size on average, meaning that we have a data set size in the neighborhood of 300 terabytes It's actually quite a bit more than that for various reasons. Each of these tracks that we have will have, some of them will have multiple versions of the audio track because labels will resend tracks to us. So we actually have at least more than 500 terabytes of data that we want to fit into this cluster. Obviously, some of this is extremely long tail. It's content that is basically never listened to, and we might not want to fit that. But we want to fit a significant part of this data set into our caching layer. We also have a redundancy factor so that if individual servers break, which they do all the time, we have some redundancy, and a secondary server will take over. I'll describe how that works, but that also means that the data set grows a little bit. We need to have more space. This service doesn't actually feed that many requests. It peaks at somewhere in the neighborhood of 60,000 requests per second, but it pushes a fair amount of data. So it pushes 60 gigabit per second of data. Obviously, since we have 11 terabytes of disks and a data set of 500 terabytes, we can't fit this on the single server. So we have a sharding mechanism. And it's based on a distributed hash table. So basically I'll describe the mechanism. You might be familiar with the ring. So if you're using Cassandra or read the Dynamo paper or using REAC, or many products are using this hash-based ring for describing a distributed hash table, and we do as well. In our case, we use SHA-1, so this ring that's not readable at all. This ring will actually start at 0 and it will end at a very large number, the largest SHA-1 hash. On this ring, we'll place our servers. So in reality, there will be 50 or so on each of these rings. We don't use vNodes or anything like that, which Cassandra, for example, supports. In reality, each server might be placed multiple times on the ring, but that's for more practical reasons. We could do a vNode setup where you have multiple, like hundreds of replications, hundreds of nodes for each physical node on the ring, but I'll come back to why we don't actually need that. On this ring, each server will own its share. So the server marked in green will own that area marked on the diagram. So anything that fits into that part of the ring will go to that server. So then if we look at an individual request, this is not, it's not that readable, but it doesn't make that much difference either. So that's a request for a particular audio file. In reality, that will actually also be a SHA-1 hash, but it doesn't matter. That path will be hashed, so we will do SHA-1 of that hash. It will turn out to that SHA-1 value or integer for that will fit in that part of the ring. Again, be owned by that server, and it will be served by that server. I'll go back a little bit to what happens in more detail when we serve that data. And in the case of a node being down or unresponsive for whatever reason, what we will do is that we will actually rehash this. So we will take a hash of the hash and find a new place in the ring and use that server instead. And this is actually why we don't need vNodes like Cassandra uses, for example. So in the case of Cassandra, if that node would have failed, we would look at the next node in the ring and use that, meaning that that new node would own its space and the failing node space being a large part of the ring. And then you use vNodes so that you will get a smaller part and they will actually fail to multiple different servers. But since we do this rehash algorithm instead, we don't actually need vNodes. And we actually describe all of this in DNS. This is a little bit of a weird part, but Spotify has, since its very beginning and still does, use DNS for service discovery. So every service that should find a different service in our backend will use DNS SRV records to look that up. I don't know if you're familiar with SRV records, but basically regular DNS records, A records, so you will use a host name to look up an IP address. SRV records are a bit different in that you will use a service name to look up a set of host names and ports. I'll show you how it works. And we use that for all service discovery. And it will also be used in this particular case. But here we also use some additional mechanisms in DNS to describe the distributed hash table as well. And we have a very well built out DNS infrastructure, obviously, since we're very much reliant on it. We run a caching DNS resolver locally on every server. So we use a product called Unbound, which is awesome if you're a heavy DNS user. So instead of having servers go to an authoritative DNS server like Bind or whatever you're running, it will actually always do its request towards localhost, and Unbound will cache results according to the TTL, and then look up that into the authoritative source. And it can actually even do pre-lookup. So if something is about to expire, it can go look up that to have that ready when there's a request for it. So looking at how this works in practice, so in this case, Dig is just a command line tool to do DNS lookups. And we look up the service name called Spotify storage on the protocol HTTP, and then lon3spotify.net is part of our data center in London. So our data centers are divided into what we call pods, which is a predefined set of servers, a size, basically a bill of material for building part of a data center that we use. And this will return a set of hosts and ports. So the third column is the port. The first and second columns are priority and weight. So you can use this for load balancing as well. We don't actually use that for the storage cluster, but it's possible with SRV records. The actual lookup will not look, this is slightly edited for simplicity, but it will actually do a round-robin mechanism as well. So this is the first thing. A client of the storage cluster, this is the first thing it will do. So it will know that I want to look up where the storage service in the LON3 data center lives, and it will do this exact request. And get back a long list of nodes for the storage cluster. The second thing it will do is it will actually look up the general configuration for the DHT ring. And that's, again, another DNS lookup. Again, we use a service name. In this case, it's config Spotify storage and so on, the same as before. And we use a TXT record. So TXT records is basically a DNS hack to just fit any TXT and any string into DNS record. There are people doing funny things with TXT records, including serving like websites, but that's a separate thing. And back we get a configuration for the DHT ring. Again, this is slightly edited, but it says a few things about how this specific ring works. So the first line says that we have a number of replicas, or the redundancy factor. And it actually says that for images, we use 9 slaves, meaning 10 as redundancy. And for anything else, we use 3 as the redundancy factor. And redundancy based on host, we can use host or node meaning host and port combination. The hash use the SHA-1, and we can provide a bunch of other configuration options here as well to configure this specific ring. And the last part of the service lookup is to actually find the tokens for each node. So in the first request that we did for the SRV records, we got back this list of host and port. Using that, we can now, for each of those combinations, see what part of the ring does this particular node own. So if we request this for this particular node, we'll get back that it owns this. Well, it's placed in these 2 places on the ring. For practical reasons, we have some tooling that when we move servers around in the ring, that would try to optimize so that we move as small part of the ring as possible so that we don't get cold content. That means that at times, nodes will be placed at additional parts of the ring. So this particular node is in 2 locations, but it might be everything from 1 to a lot of locations in the ring. So again, a client, in most cases for audio storage, the access point that I described before, this perimeter service, will do this lookup, build up a representation of this ring, so it will know that for each request, it can actually hash this and get a a node that will serve this particular file. Yeah.
Since you're using DNS, do you run your own Nginx DNS or do you use it provided?
For DNS?
Yeah.
No, we run our own actually. So within our data centers, we use Bind as the authoritative DNS server. Well, actually, we use a combination of Bind and Power DNS as the authoritative DNS. For our external stuff, so how clients find the access points, for example, we use Dyn for GeoDNS services. No, this runs in, well, 4 physical data centers and in actually 7 different clusters, storage clusters at this point. When I say 4 different data centers, that's actually not really true as well, because like in London, for example, we're actually using 2 separate data centers, but they're deployed as a single, from a Spotify developer perspective, as a single entity. The upstream, I mentioned before that Nginx runs as a reverse proxy, and previously, to do all of this DHT magic, we actually used a custom Nginx hack or a module built into Nginx to do all of this, the DHT stuff. That turned out to be a little bit messy over time, and we ended up being on a very old Nginx version for a long time because no one really wanted to touch this somewhat scary code. So what we do now instead is that Nginx runs as a just vanilla reverse proxy, and on localhost we run a separate process which does this part. And which is built like a typical Spotify service would have been built. Which means that we can now actually run on a very new Nginx or keep up with Nginx releases in a much simpler way. All right, so to describe this in a slightly different way, I'll walk through how a request to the storage server, a storage cluster works. So again, we have this client, and we have the access point, and within one of our data centers, we have one of these rings. And a request comes from the client for a particular audio file. Again, we hash it, and we find this node that will serve this data. If this node happens to have this file cached, which we obviously hope it will, and try to optimize so that it will do, it will just return that data back to the client, and fast and simple. If it doesn't actually have the data, so we have a cache miss in that node, what will happen is that this service that I mentioned running on localhost will make a rehash to find the secondary server for this particular file. And we'll go fetch that from that server. Again, if that has that file cached, it will just return it back. If it doesn't, it will go fetch this file from origin, so from Amazon S3. There are actually some additional services involved to make that to add some redundancy into that, but that's not part of this talk. The thing with this particular way of doing it, going to the secondary node, means that we have some amount of heating of that secondary node. So if the first node fails, the secondary nodes will also have a part of that primary node's files already available, meaning that it's sort of already heated. Of course, those files might get evicted because this is an LRU cache. So if that node, it will obviously get more requests for the files that it's the primary node for. So it might evict these nodes, but it always has some part of the files that our primary node in this example will serve. So if that fails, it will be partially heated, which is a very good property of this setup.
How do you update this ring as new files get in?
Sorry?
How do you update and keep rebuilding the ring as new files get pushed to the cache?
Well, any new file will just be hashed to some other part of this ring, and it will go through this process of going from master storage into the cache. Did that answer your question?
That happens like what, every day? You do like a mass push of files?
No, so files are always pulled from master storage. So files will be fed into master storage continuously during the day as we receive them from labels. And whenever our metadata for these files goes out, so the clients actually knows that these files exist, we will get requests, but then they will be pulled through this process. So we don't need to push files. Yeah. Yep.
So if you have a node failure, in a case with 6 nodes, there's still a 1 in 6 chance that you can't find it on the secondary because the SHA-1 and the SHA-1 will be on the same node. In that case, does the AP go direct to master storage, or what do you do in that failure?
That's actually the next couple of slides. So no problem. So if we have a node failure, so if this particular node fails, again, same example, what will happen is that the AP will detect this. It can't connect to the server, or it times out, or it gets a 503 or whatever is defined as a failure. The access point will rehash this again. So we'll take the SHA-1 of the SHA-1, take the secondary node and retrieve it from there. Again, there's a slight chance that this file already exists on that node because we've made this request in the last example, meaning that this is already partially heated and ready to go to serve these files. Again, since the SHA-1 of the SHA-1 will distribute over the entire ring, all of the additional 6 nodes or 5 nodes will actually pick up this traffic from this failing node. And the access point will actually blacklist and start probing this failed node. So if that node is just temporarily down, or we restart it, or whatever, it will just be blacklisted for a short while and then probed. And when the AP discovers that it's back up, it will traffic will get routed back to that node again. But for some time, we can actually handle node failures without any user experience, any user noticing. This was actually the case yesterday during some of the talks here. One of our nodes in San Jose failed, and APs blacklisted that, and operations continued as expected. Did that answer your question, by the way?
Not yet.
Okay.
Next slide.
No, it might not. So rephrase the question, and I'll try to.
What if so the SHA-1 of the file is on node 3, and the SHA-1 of the SHA-1 also is on node 3?
Ah, yeah, sorry, yes. So that's actually a real thing that happens. We have a redundancy factor for audio files. We use a redundancy factor of 3, meaning we will actually do this 3 times. And in reality, we have 50 nodes. So that means that it will have a 50 to the power of 3 chance of doing that. And we've defined that as an acceptable level of errors. But it is true that there will be a certain amount of requests that will fail, that will hard fail to the client. All right.
So does this sort of work better than the Cassandra style of the next node wraps the content? Why did you pick this versus that?
That's actually a very interesting question. This algorithm has been around since before Cassandra, and I think it was sort of designed around the time that the Dynamo paper came out. So I think it might have its historical reasons as well. A nice property compared to Cassandra is, again, that we don't need to have virtual nodes to manage this, the failure state. But we actually support, I think I edited that out in the configuration, but in the DHT configuration that we get from DNS, there's actually an attribute for what algorithm we use for the ring. And we actually support consistent hashing mechanism, which is like how Cassandra does it. That is actually not implemented in the access point though, but so we don't actually use it.
The other nice thing about that is that when you resize the ring, for the nodes that didn't drop out, you only get 1/n records that end up in these spots.
Yeah.
Your cache is also increased with no errors, even though you change the ring.
All right. Oh, sorry, wrong slide. So some of the performance trade-offs or performance attributes of this setup, or things that we need to do with to get the best performance out of this. One of the things is that for page caching, we obviously want to use the page cache as efficiently as possible. Reading stuff from memory is faster than reading it from disk. One of the things that we noticed is that when we use, since we have sort of large files, 5 megabytes, we would trash the page cache by basically, we would fit very few files into the page cache, not being very efficient with it. So a thing that we do, and this is a hack in our in the Nginx that we use, is that we use Fadvice to tell the operating system to only page cache the first 64K of the file. Again, we're very focused on the playback latency, and this allows us to read 64K of the file from memory, and then we'll go get the rest from disk. 64K is picked based on the approximate amount of data that we need before a client decides that it will start streaming or start actually playing the song. So when the client starts downloading audio data, at some point it will use it will need to decide that I have a sufficient amount of data in my buffer that I can actually start audio playback without getting an audio stutter after a few seconds because it runs out of data. And the clients actually use a Markov chain-based algorithm to do this based on previous bandwidths from previous streams and so on, and tries to find the best size. But since in this case we can't actually rely on getting that data back from clients, we use 64K as an approximation for how much buffer we need in clients. And just sticking 64K of data from each file into ROM means that or into the page cache means that we can fit a very large set of the files that we have on the server into page cache and get a good latency from them. Another interesting discussion around this, and you can actually see this in the DHT configuration I showed before, is that what should be the redundancy factor and how should we spread traffic to the nodes. So we actually have an option to, instead of using this hash and rehash mechanism to find all the nodes that are responsible for a particular file, we also support using round robin. So when the client, the client of the storage, the access point typically, gets a request, it can either always use the primary node, as I showed in the example, or it can round robin over all the nodes that is responsible for that file. And we actually use that for images and client upgrades, which is also served from these clusters. And the thing with, in particular, images is that we have an amazing ability to DDoS ourselves in various ways, and we've done it multiple times. And a very typical way of doing it is that in our desktop clients, we had, I don't actually know if we have it anymore, but we had this activity feed on the right side showing whatever your friends listened to or playlists that you followed if they were updated. Thing is that some of these playlists were extremely popular and had millions of followers. And when someone updated that playlist, it would be immediately broadcasted to everyone who was online and was a follower of the playlist that this playlist has now updated. And in that activity feed, we wanted to show some sort of picture of that playlist, and that was typically album covers, which is served from this cluster, meaning that we could get millions of requests for a particular file within a few hundred milliseconds. And that's a very, very good way to overload a particular node in a storage cluster. So what we do for images instead is that we actually round robin these to a bunch of servers. That for audio files, that wouldn't actually work that well because we would get a low cache locality, because then we would try to fit each audio file on, say, 3 servers, meaning that we would fit a smaller data set in total in our cluster. So for audio files which are larger, we want to use this mechanism that I described before, having a primary node that will always be requested, which will have a very high cache locality for that particular file. But for client upgrades and for images, we'll spread it over the entire ring or over a larger set of nodes. Client upgrades are far fewer files, and usually it's just one file one file per operating system getting requested a lot at any given point in time. And images are small, so even if we have a larger redundancy factor for images, we can fit a lot of them into our storage. It works very well. It means that we can also survive these DDoS attacks that we apply on ourselves. There are a number of pitfalls with this setup. I'll describe, well, just one of them for now. If you have any questions, I'll be happy to answer them. The major pitfall that we have at the moment is that scaling this storage or this cluster out means that we also need to scale out the access points, because this is bounded by network bandwidth. So if we double the number of nodes that we have in the storage cluster, we will run out of bandwidth on the access points, so we need to scale that up as well, and it makes this sort of expensive. That is actually something that we're going to address in the next few weeks by a redesign of how this works, but that's the case at this point. All right, I'm sort of running out of time, so any questions?
Are the storage nodes just Nginx web servers with local file system?
Yes.
Right.
Yes.
So there's a Nginx running there, and you use the file cache, Nginx's file cache, or
Yeah, exactly.
that's
So
the
it's
cache that you're running.
no, it's a bunch of disks. It's a RAID array attached to that local machine with a bunch of disks. Running Debian, we're in the process of moving from Debian Squeeze to Trusty, Ubuntu Trusty, but running Linux in some form, and Nginx. It's a very simple setup, which we like. Any more questions? I'll be around over lunch as well if you have any additional questions afterwards.